and welcome to Living Proof, the joint podcast from plus.maths.org and the Isaac Newton Institute. I'm Rachel Thomas.
I'm Marianne Freiberger.
And I am Sarah Khan. So in this podcast, we hear from Adina Goldberg, a PhD student at Waterloo University of Canada. Adina has been a participant in the longer research program at the INI last year. She uses maths to research quantum information theory. What is that?
So now we're all aware that we can store information in physical systems. So you can write it down in a book, or you can make an audio recording like this one, or you can film a film. And we also know that these days a lot or most of our information is encoded in computers. They are also physical systems. And within a computer, though, information is encoded in zeros and ones, and these bits of information are called bits. The digital information that we use and that we exchange every day happens through the storage, the manipulation, and the transmission of these bits of information. And now, as many people may have heard, there is a sort of potential revolution in the making, which involves bringing quantum theory into the picture. Now, quantum physics describes the world at the smallest scales. And the theories at that level are very strange and quite counterintuitive and quite complex. Now, storing, manipulating, and transmitting information as quantum bits, also called qubits, in quantum computers opens up a whole new world of possibility in terms of what we could compute and how we could communicate.
So we'll put some links to some introductory information about some of these ideas in the show notes. So the area that Adina works in is called quantum information theory.
What maths does she use?
So it's interesting, the ideas, because it's got so much physics, and actually what happens in this really theoretical physics, even when it comes into applications like quantum computing, it's still driven, a lot of the discovery and the understanding is still driven by mathematics and the mathematical descriptions of what's going on. So what she uses is something called operator algebras, which essentially studies a generalization of something called matrices and how they behave. And matrices you can just think of as grids of numbers that encode how things can be moved about in space. And she also uses another area of maths called category theory, which is a really abstract way of looking at how different structures are mathematically related to each other. But what I found so fascinating about talking to Adina about her work is that she uses diagrams to explore these really complex mathematical ideas. I spoke to Adina over Zoom when she went back to Canada, so the sound is a bit dodgy, so apologies for that. Here's Adina.
So most of the ideas from category theory that I'm using have been developed through this area, this newish area called categorical quantum mechanics. And a lot of the techniques in that area, part of why I was attracted to it, are their graphical techniques. So when I start thinking about using tools from category theory, I'm usually thinking about using these specific tools where I can draw an equation as like a two-dimensional diagram on a page. And then that helps me think about like, okay, how can I compose it with other things? What properties does it have? How can I connect that process? So these diagrams represent processes. That's one way to think about it. How can I compose that process with other processes? How can I show that it's actually the same as doing something else? And you're always using these properties that come from the level of category theory, but the actual day-to-day of it, you're just using the rules of how to manipulate these diagrams.
So these diagrams, what do they look like?
They look really surprisingly simple. They look a lot like graphs if you've seen them in maths, which are basically sort of networks, edges connected by nodes. And in fact, Adina uses ideas from graph theory in her work. And one thing to understand is the diagrams represent a process happening in time. And you actually read the diagram by starting at the bottom of the diagram and going up the diagram is equivalent to moving forward in time. And sort of the simplest diagram consists just of a line from the bottom to the top, or what Adina calls a wire. And this could represent this sort of classical bit that Marianne mentioned, a 0 or a 1 that we use to encode information in computers today. And in that case, just a line going from the bottom to the top of the page on its own essentially represents that nothing is happening to the value of that bit over time in that diagram. It's just unchanged. But obviously you can make things really complicated. You can add nodes to the wires or connections between the wires, and this starts to represent transformations of the wires which allow you to sort of capture the behaviour of manipulating a bit or a qubit. Here's Adina again.
The simplest wire that you can think of would represent, well, the simplest wire you could really think of would just represent like the classical set of two numbers, which really represents a bit, like a classical bit of information. And you can contrast that with the behavior of a sort of like quantum set of size 2, which would represent a qubit. And so you want to think about the different behavior of these two different wires and the mathematical sort of like relationships that they have, and the equations that you can write down with the diagrams sort of capture the physical processes of trying to copy bits or qubits, trying to delete bits or qubits, trying to measure bits and qubits. All of these things are captured by like the graphical rules.
Well, that's so interesting, isn't it? That such kind of complex ideas in quantum physics, which, you know, we'd need to study for years to really understand, that sometimes you can express or capture these things by deceptively simple diagrams. And then you can understand problems in these complex systems using these diagrams without really worrying about the underlying processes. So we've come across this before, right? So there is something that people might have heard of called Feynman diagrams, which were invented by the physicist Richard Feynman, which very kind of accurately and interestingly capture the interactions between little particles, which are obviously governed by quantum physics.
And you can actually use the Feynman diagrams, just like you can use these, to make calculations, which I just find amazing. The idea that the diagrams aren't just they really give an intuitive idea of what's going on, but they also are a method to understand and do mathematics with these diagrams. So you really benefit from translating these ideas in quantum physics into diagrams. So it gives you this intuitive way in, and it gives you, I think, an intuitive idea of the sort of processes that are going on. So we asked Adina if there was something about quantum information theory that you can capture in a diagram that gives you a more intuitive way of understanding what's going on than just learning it through equations alone. Here's Adina.
Yeah, so I'll say two things. The first thing I'll say is that quantum information still relates to classical information theory and sort of electrical engineering ideas like circuit diagrams, which are very useful tools there. So representing your system as a process and having rules for how the process behaves, sometimes you just need more space than a single equation with these like letters that you can't always tell apart on first glance. Sometimes it's easier to just look at it with more space, right? And that idea also relates to physics, because the first sort of physics diagram I ever saw was a light cone diagram. And you sort of need the two dimensions there. You need to at least have like a time dimension and a space dimension in order to make sense of the idea of light cones. And it's kind of similar here. You need to have, you need to be able to compose quantum systems in two dimensions. And an equation isn't enough for that. You end up with all these indices all over the place, and it gets very difficult to read. You can do it, it's just hard to read. Whereas when you put it as a diagram, you have sort of this spatial composition, which means putting systems sort of next to each other, like composing systems. And you have this sort of time composition, which happens from, well, somebody just told me recently that this is the optimistic convention, to read it from bottom to top.
Yeah, so when we talk to mathematicians working in different areas of maths, it's so interesting that the perspective that they bring, you know, the way that a person might write something down or the way they might draw a diagram, how those different approaches can really clarify the ideas that people are trying to understand. So it's bringing different approaches to a thing that is so useful.
I think that's really part of the skill, isn't it, of being a mathematician, is figuring out the right language, whether it's equations, diagrams or some other method to communicate in. Here's Adina again.
A lot of the research I'm doing is not really new in the sense that other people have worked on the same ideas or done similar constructions, but a lot of the ideas I'm presenting have never been presented in this diagrammatic language before, and it really clarifies and changes, I think, the key takeaways people get from thinking about and looking at these ideas.
When I was researching things before I interviewed Adina over Zoom, I was really intrigued by something she had written on her website. She has this motto on her website, and the motto is, "The meaning is in the arrows." I asked her what that meant.
I'll just say that I was just thinking about this yesterday. So I was thinking about the fact that when we describe quantum states in the sort of conventional formalism of quantum mechanics, we describe them actually best by operators. They're these density operators, so they look like a matrix. And operators are things that act. They're sort of represent processes or transformations. And I'm not a physicist, and I have not, seen a lot about the different interpretations of quantum mechanics. I've seen some, but just from the formalism, I had this feeling that really states should somehow be thought of more as like a stable transformation or a stable evolution than as like a static thing. And that's kind of the same ideas that got me doing what I'm doing right now. The fact that you should be thinking of all of these things as processes, not as these static blobs. And so the meaning is in the arrows. I would say loosely it means that there's objects that are just reference points, and those could be people, those could be places, those could be mathematical objects. And the arrows describe either relationships between people or journeys or structure preserving transformations in the case of math. And so essentially, like, I guess points or objects are just references to put arrows between, and everything's relational. That's kind of my perspective. Although I will say that recently I've been learning about this idea of contextuality in quantum mechanics. And what that's telling me is that maybe I actually do care a little more about reference frames than I originally thought with this motto. Maybe they're more important. So maybe I'll have to change it. Who knows?
The meaning in the arrows, such an interesting idea given the work she does with these diagrams describing the transformation of quantum information.
It really is, isn't it? And it's also interesting given her kind of personal experience. She started off in engineering and maths, then she taught computer science, she's come back into maths and now doing quantum information theory. She's really moved through lots of different areas and led a really interesting career.
So maybe her motto captures the idea that the interesting stuff happens in the process or in the journey rather than the destination or in the transformation. And that's true whether you're talking about quantum information or about careers.
Exactly. So we met Adina through the QIA research program at the Isaac Newton Institute, which was into this area of quantum information last year. And one of the reasons we ended up talking to Adina was because she mentioned to our colleague, Claire Merritt from the Newton Gateway, who organised an Open for Business event during the program. Adina mentioned to Claire that she was really interested in how storytelling could be important to research mathematicians. We asked her, how can storytelling help with research?
So I've been to a lot of research talks in different areas of math, engineering, quantum theory. And the ones that I walk away from where I actually feel like there's a question I want to know the answer to, or where there's something I might be able to work on, are always the ones that have told a story in some way. And maybe it's not like outright, like here's Alice and Bob and they went to the diner and, decided their strategy for this game they were going to play. But maybe it's just, something motivating, something well structured, something very well communicated. and where I walk away with like a feeling that there was a journey that we went through throughout the talk. And I think this can be taught. I think some people have a feeling like some people are good speakers and some people are not, but I think this can really be taught. And I think being able to communicate your research in a way that captivates your audience is not like a luxury. It's not like some sort of extra thing that, like, we would do if we had the time or the money. I think it's actually fundamental to getting your research across to other researchers and forming connections with them.
Yeah, so that sort of reflects something that we think about a lot, because when we communicate mathematics by writing articles or podcasts or even thinking about TV series, or when we teach communication of maths, we often think about how important it is to find a narrative and to map out a story from beginning to end with the stepping stones in the middle. So this kind of rings very true to us.
Adina came to the programme at the INI with her family. She brought her child and she came with her spouse. And she said that was only possible because of the help that the INI could provide. They did things like they provided an apartment for the family to live in together.
Yes, you see, as an international research center, the Newton Institute is really committed to removing barriers to participation and making it easier for mathematicians to join their programs. It has various support schemes, such as the childcare support, as well as other forms of financial support for mathematicians, especially those working in low and middle income countries.
I think it's so important that the INI does this. It must broaden the kind of people who can come along. And Adina said the environment that you come to, particularly as a long research program at the INI, is so unique. This chance to come and work with people face to face over the course of the program, that was really a massive draw to her. And particularly so because she was coming to the program after this sort of period that we all went through of sort of isolation we all had of working alone during COVID. So that was even more attractive to have this opportunity to come together with people to work together on this shared area of research. And I think one of the aspects that Adina mentioned that so many researchers visiting the INI mentioned is this chance to interact both formally through seminars and workshops, but also informally, sort of over coffee or at dinner or going for walks. You interact with researchers in that way. It produces some really interesting insights for all of them during the program. Here's Adina again.
I'd like to tell a story about a really funny thing that happened during my visit to the Institute, if you don't mind.
Yes, please.
So I brought my spouse, who's also a mathematician. He's a graph theorist, which I never thought our work was connected at all. Maybe I had a suspicion that there was something quantum-y about something he did in his thesis defense, but it just so happens that during the program, we met an individual who ended up telling us that he was working on a problem that exactly used the previous paper I had written, but also was trying to solve the same problem that my spouse is working on at the moment in graph theory. And it was just amazing. Like, it wasn't a direct connection. There was he had to come to our apartment and tell us the rabbit hole of, 14 steps that connected mine and my spouse's research, but that was a really amazing moment for me.
Oh, that's nice. I suppose that is what is so nice about the opportunity of attending something in person, like the program at the Newton Institute, is that you have the chance to have these unexpected conversations with people and making all these connections.
That's right. And Adina also said it's this sort of unusual structure of these long research programs where there's this generosity of time and space for both the formal and informal interactions, that was a real highlight of the experience of attending the program for her. So she was saying you might hear about research in a formal seminar, but you can also connect with someone over a cup of coffee or standing at, one of the famously numerous blackboards around the INI again. Here's Adina again.
I just wanted to say again that the structure of the program was really unique and special. I've been to one or two other extended programs before. In one of them, it was more you just worked with a mentor very closely, and that was the focus. In the second one, It was really more of a school that was intended to train graduate students in quantum information. But this was unique in that I'd really never had the time to have coffee every day with the same niche group of researchers who, for the first time, were actually like the exact audience I was looking for to talk about some of the work I was developing. And I was scared to give a talk. I didn't feel like my talk at the end, fine, conference talk, but I wasn't sure about giving the sort of unstructured talk where I just propose problems in front of all of these experts and see how people react. And it was one of the most amazing experiences of my PhD. I got into a room. I didn't expect anyone to show up. I actually told them not to list my talk publicly because I didn't feel comfortable. And I said, okay, it's just informal, maybe, a few people will come. We'll just chat for 2 hours. And a large percentage of the people at the program actually came. They sat down. I talked for an hour. And at that point, I kind of was like, okay, do people need to go? Maybe 1 or 2 people left, but most people were interested to finish the story, and it was really gratifying.
That was Adina Goldberg. We'll put links to more information about anything we've talked about today in the show notes.
So that's it for this episode of the Living Proof podcast. Thanks very much for listening. If you like the podcast, then please recommend us to a friend or subscribe or rate us on the platform that you're listening to the podcast. It really helps other people find us. Thanks for listening and bye for now.
Bye.
Bye.